It's time to begin a journey into higher order differential equations. And before we get into solving any higher order differential equations, we need to understand some basic theory that we'll encounter. The first thing I want to look at is called the existence of a unique solution when you're dealing with initial value problems. Now remember, an initial value problem is something like this, where you have a differential equation, okay? And you notice you have these derivatives here, okay? This is just a general one. Actually, the y is not a derivative, and you have the coefficients, 4x squared here, 2 here, 7x here, and 2 here, and so forth. But this is a higher order differential equation. In fact, this is a third order. And you have down here this initial conditions, okay? So you have y of 2 equals 3, y prime of 2 equals 5, and y double prime of 2 equals 4. So we're saying, okay, at this value for x, we have these conditions, 3, 5, and 4, for the corresponding derivatives there. Now, in general, though, I wrote the general expression here where you have this a sub n minus 1, and so forth. Those correspond to these numbers in front of the derivative, and they are functions of x. Of course, a with the little n up here, that's the nth derivative, n minus first derivative, and so forth. So here you have a differential equation. And down here you have the initial conditions, or the initial condition. And notice I'm putting in an x naught into each one of these. Okay, this is an initial value problem. Now, I want to point out some things here. Some conditions for this theorem to apply that I'm going to bring out. These coefficients, if this happens, if every one of these coefficients, which are functions of x, plus this value on the end here, if these are continuous on some interval containing x naught, okay, so we have an interval containing x naught, and these functions are continuous on that interval. Okay, so that's the first condition. Also, this a sub n, this coefficient here for this highest derivative, it doesn't equal 0 for all the x's on that interval. Okay? Okay? When this happens, and let's suppose x naught is in this interval, it's one of the values for x, the solution, that solution exists when these conditions are met on that interval, and it's unique. So let's just look at an example here, because that's kind of a mouthful. But if you look at that, let's look at a particular example. Here's y double prime minus 4y equals 12x. Now that meets all of the conditions. The coefficients of these derivatives are, they're continuous. They're just numbers. You got 1 and negative 4. And 12x is certainly continuous. Now, the initial conditions, the initial values that were given are right here, okay? Y of 0 equals 4 and y prime of 0 equals 1. And this right here is the solution. Now, that is the only solution. That's what this theorem is telling us. That is the only solution because all the conditions are met. Now, you might be wondering, is that really a solution? And what does it mean for it to be a solution? Well, let's take a look here. Let's see how we would verify that this is a solution. I'm going to find the derivative. So this is going to be 6e to the 2x minus 2e to the negative 2x. Okay, that's the first derivative. The second derivative is 12e to the 2x plus 4e to the negative 2x, okay? And for it to be a solution, I need to take y double prime minus 4y and that needs to equal 12x. So let's see if it indeed does. We've got 12e to the 2x plus 4e to the negative 2x. And we're subtracting 4 times the initial solution, or the y value. So this is 3e to the 2x plus e to the negative 2x minus 3x. And let's see what that equals. Here we go. Now this is minus 12e to the 2x minus 4e to the negative 2x plus 12x. Now, let's see what we got here. These cancel, and all we're left with is 12x. Yes. So, yeah, we verified it, and we know that's the only solution. That's the only solution. Now, I want to look at this next one. Okay, so we've got an initial value problem here, and notice we're plugging in a 0. But at 0, this term over here, this coefficient of the y double prime is equal to 0. That condition is not met. So that theorem that we looked at over here, that if it meets those conditions, we have a unique solution for that initial value problem. That condition is not met, so that theorem does not apply. Now you may be wondering, well, why do I need to know this? I can just solve these differential equations and find out what the solution is. Well, look at this one. Here is 3y double prime plus 5y, triple prime, plus 5y double prime minus y prime plus 7y equals 0. And you notice that you've got y of 1 equals 0, y prime of 1 equals 0, and y double prime of 1 equals 0. And you're trying to, what you want to do is you want to find the solution. Whatever method you're going to use, you're going to have to find the solution. You're going to have to put in some work. But if you know that there is a unique solution, and you know what that solution is from the beginning, you don't need to put in that work. Now, notice that this is we're going to talk about this more later, but this is a homogeneous differential equation. And notice one of the solutions, or the solution for this differential equation, is y equals 0. That's definitely a solution, because if y equals 0, if y equals 0, the derivative of y is 0, the second derivative of y is 0, and the third derivative of y is 0, and that is certainly a solution here. So we know that, that's going to be the only solution, because we're told when y of 1 equals 0, y prime of 1 equals 0, y double prime of 1 equals 0. So, in other words, y equals 0, there's no point in trying to find coefficients or anything like that, or going through the process. You already know that y equals 0 is the only solution. You don't need to work on it anymore after that. Okay? So that's why knowing this information up here can be helpful to you, because you don't have to do any work. They're just saying the trivial solution, y equals 0. Yeah, I knew that already. Now, I want to go down here and make a distinction, because up here we're talking about initial value problems. And sometimes there's some confusion about the difference between an initial value problem and a boundary value problem. Okay, so this right here is an initial value problem, where I'm putting in a 0 and getting out of 1. I'm putting in a 0 into the y prime and getting out of 4. This over here is a boundary value problem. Notice I'm putting in a 0 and then I'm putting in a pi. I'm putting in different numbers there. So on the one hand, I have an initial value problem. And the initial value problem is what we were just looking at for that theorem. the existence theorem, the existence of a unique solution theorem. Now I want to show you how these can differ, because if you look at this first one, this initial value problem, this definitely meets the criteria for the uniqueness, a unique solution theorem that we just looked at. In other words, this meets the qualifications. And what I'm saying here is that this is a solution. Now I haven't found the coefficients yet, but this is a solution. Now let me go through here and work this out and show you what I'm talking about here. So I want to first of all, I'm going to verify. Actually, I'm not going to verify this is a solution. Let's take that as a given, okay, for time's sake. But I do want to find these coefficients. Now, first of all, it says y of 0 is equal to 1. Now, let's see what that gives us. We get 1 equals C1 cosine 0 plus C2 sine 0. Okay? Now, when we do that, we get, of course, this over here is 0, okay? But we get C1 is equal to 1, okay? So C1 is equal to 1. So now let's go and look at C prime of 0 equals 4. So, or y prime of 0 equals 4. So here goes y prime. Okay, so y prime is going to be negative 2c1 cosine, sine 2x, there we go, plus 2c2 cosine 2x. Okay, now when I put in a 0 there, y prime of 0, I'm told I get a 4. So here's what I get. I get 4 equals negative 2c1 sine of 0 plus 2c2 cosine of 0, which is 1. So I get this. I get that c2 is equal to 2. So I now know my solution for this initial value problem is going to be cosine 2x, see, putting a 1 in here, plus 2 sine 2x. Okay? And that is the unique solution for that initial value problem. Okay, now I want to look at this boundary value problem. Okay, so let's take a look at this one. Let me move this up a little bit. And I still, I get this. I get that y equals c1 cosine 2x. This is just the general form that we have. Okay? And what I want to do, let me give myself a little more room here. I want to shrink this down. I want to see if I can figure out what these coefficients are. So first of all, we're told that y of 0 equals 0. So here's what we got. I plug in a 0. And of course, that's, plugging in a 0 into this sine part gives me a 0. So I don't have to worry about that. Now this gives me that C1 equals 0. Okay, there you go. C1 equals 0. Now I need to figure out, plug in the pi, okay? So here I go. I'm going to plug in the pi, and into my solution. Now, here's what I've got so far. I've got 0 cosine 2x plus C2 sine 2x. And I'm told that at pi, I get a 0 over here. So I get C2 C2 equals sine of 0, okay, which is equal to 0. Oh, look at this. We got 0 equals 0. Now, okay, so let's think about this a second. When we found that C1 equals 0, we were left with this thing, y equals C2 sine 2x. That's what we were left with. And we found that when we plugged in a 0, we got out a 0. Yeah, of course. Well, look at what this looks like graphically. Okay. What I've done here is I've graphed y equals C2 sine 2x. And this right here is when we have y equals sine 2x. In other words, when C2 equals 1. This one is when we have y equals 1/2 sine 2x. And this one right here is when we have y equals 1/4 sine 2x. Now, you see that there are a lot of options for this particular graph. Now notice it says y of pi equals 0. Well, look. Now notice these initial conditions. Y of 0 equals 0, right there. Yes. Condition met. And then then it says also y of pi equals 0. Well, oh, I was marking the wrong thing here. My eyes. Y of pi equals 0, right over here. So notice, in every one of these that I've graphed, and I could graph a lot more, they do have this condition that y of 0 is 0 and y of pi is 0. So we would say, yeah, for those conditions, there's an infinite number of solutions. See, we established C1 is 0. That left us with just this term over here. So I'm going to graph that and see, I'm just going to explore that part of it. And since it says y of pi equals 0, well, that's any of those graphs. Any choice for C2 will work since it's equal to 0. Okay, I hope that's clear to you. But this just shows you that sometimes, so we have a boundary value problem here. Now notice this is not an initial value problem. This is a boundary value problem. It meets the conditions of that existence of a unique solution theorem. However, this is not an initial value problem. This is a boundary value problem. I'm putting in a 0 and then I'm putting in a pi. Now let's look at a little bit different down here. Let's suppose that we say we have the same condition y of 0 equals 0 and y of pi over 4 equals 1. Now if you look at that one and you, same thing, C1 is equal to 0, so we're just considering this part. You can see that here's pi over 4 and we're saying, okay, when does this equal 1? Well, only for this curve right here. See, here's where it's equal to 1 up there. Okay, so C2 would have to equal 1 on that one. See? Now, let's look at this one this next one, this one right here. Here we have y of 0 equals 0 and y of pi equals 2. Okay, so once again, we're looking at this part of it. I'm looking at these graphs. And it says y of pi equals 2. Look at these solution curves. These solution curves all end up at 0. At pi, they all end up at 0. There is not one of these curves where you would end up at 2. Yet, this is the solution. And this is saying, at pi, the value is 2. No, it's not. It can't be. So we would say for this one, there is no solution. No solution for that one. So you can see here we've got initial value problems. That's what that theorem dealt with. And then we have boundary value problems. And that's just some things to keep in mind.